This is the end of chapter 12 lecture. We left off on Tuesday talking about type 4 reaction or molarity problems. So this was asking for the volume of some known molarity solution if you know the molarity and you're given the moles of solute. And we solved for this equation, listing what we knew, which was the molarity and the moles, and we wanted to know the volume. We left off with another example of that type of problem. If you haven't tried this yet, please pause the video and try it. For this problem, it's asking how many milliliters of a 0.5 molar sodium chloride solution to get 2.0 grams of sodium chloride. So now instead of being asked to get to moles, we're being asked to get to grams, so there's an extra step in this problem. We always, however, want to start with getting 2 moles. So we're going to ignore the grams for right now. And for this problem as well, you can leave it in milliliters or liters. See page 5 notes for why this is the case. So if we're getting to milliliters, we can convert grams to moles and then work through the problem. So for converting from grams to moles, you always use the molar mass of whatever it is you're looking at. So this is 2.0 grams sodium chloride. The molar mass of sodium chloride is 58.443 grams for every mole. If you do the math and follow sig figs, you should get an answer that only has 2 significant figures, and that would be 0.034 moles of NaCl. So now we can go through our steps as per usual. We're going to rearrange our molarity equation so that it is solving for the unknown. So we know molarity equals moles over volume. If we rearrange that for volume, we get volume equals moles over molarity. Step 2, we're going to make sure our units cancel. So if I have moles on the top and molarity on the bottom, I know that molarity is moles per liter, which is the same as writing moles times liters over moles. The moles cancel, and I'm left with volume equals liters, which checks out. Correct units. Again, going through steps 1 and 2 is not necessary in order to solve the problem. I break it down for these problems in chapter 12 and the problems in chapter 11 so that you guys can follow your thought process if you are getting confused. If you can do steps 1 and 2 in your head and you are getting the correct answers with the correct sig figs, that's fine, unless in my question I specifically ask you to show me each step. So the last step, we're just going to put in the numbers for our units. So we have the moles that we calculated for NaCl from the grams. And I'm going to divide that by the given molarity, which is 0.05 moles per liter. And putting this into a calculator, I should only come out with one significant figure, 0.7 liters of the solution. We can now move on. This is the last type of problem you're going to encounter with molarity, and it's stoichiometry and molarity. There are two types of stoichiometry, with precipitation reactions and then with acid-base reactions. I'm going to go through examples of each. So for precipitation reactions, you might see a question like this. How many milliliters of 0.25 molar zinc chloride does it take to react with 55 milliliters of 0.2 molar sodium phosphate? So again, just like in chapter 11 when we talked about the gas law, the key word for stoichiometry problems is react. So step 1 of any stoichiometry problem, write out your balanced chemical equation. So zinc chloride, aqueous, reacting with sodium phosphate, aqueous. I know it's aqueous because I have a molarity. I'm going to swap the partners, so I'm going to do zinc phosphate, zinc 3, phosphate 2. If you've forgotten how to write compounds, please go back to chapter 5. This is going to be a solid plus sodium is now going to match with chlorine. That's just one sodium for every chlorine, and that is aqueous. So now let's make sure this is balanced. We have zinc, chlorine, sodium, phosphate. 1, 2, 3, and 4. Nope, just kidding, we got 1 phosphate. So 1 unit of PO4. And then on the other side, I'm just going to list them in the same order. We have 3 on the product side. For chlorine, I have 1. For sodium, I have 1. And for phosphate, I have 2 phosphate units. We're going to balance the metals first. I'm going to start with zinc. To make them equal, I'm going to put a 3 on the reactant side. That gives me 3 zinc. And now 3 times 2, 6 chlorine. The zincs are balanced, but now the chlorines are out of balance. If I put a 6 on the product side, that gives me 6 chlorine, 6 sodium. I'm going to head back over to the reactants. I'm going to put a 2 in front of the sodium phosphate. That gives me 6 sodium. That gives me 2 phosphate units, and now everything is balanced. So here I can write in what I know and what I want to get. So we want to look for the volume of zinc chloride, and that is specifically in milliliters. From the balanced chemical equation, I know the moles of zinc, how many moles of zinc it takes to react with moles of sodium phosphate. And in the problem, I'm given the molarity of zinc chloride, 0.25. I'm given the molarity of the sodium phosphate, 0.20. And I am given the volume of the sodium phosphate, 55 milliliters. Because we want our volume in milliliters, at the end I'm going to leave this in milliliters. So I'm going to set up the unit conversions. So I know the volume of sodium phosphate, and I want to try and convert that into volume of zinc chloride. So milliliter sodium phosphate Well, in order to get from something to some other thing, the only thing we know that does that is moles to mole conversion from the balanced equation. So I need to convert my milliliters to moles first. And the way we convert milliliters to moles is the whole point of chapter 12. I'm going to use the molarity. I'm going to put 1,000 milliliters on the bottom instead of 1 liter because I am using milliliters as units. 1,000 milliliters is equivalent to 1 liter. On top, I'm going to put 0.20 moles. Let's leave the numbers out. Let's just do units. So milliliters cancel milliliters, and we're left with moles. And then I know I can convert from moles of sodium phosphate to moles of zinc chloride from the periodic table. Sorry, not the periodic table, the balanced chemical equation. Moles of zinc. So now I'm left with moles of zinc Cl2, zinc chloride, and to get from moles back to milliliters, I need another molar conversion. This time, the molar conversion for zinc chloride. Zinc chloride was 0.25 moles per milliliter. Moles cancel, I'm left with milliliters. So now I can plug and check. I'm going to add in the numbers. So I start with the numbers here for zinc chloride molarity. 0.25 moles per liter. I know that there's 1,000 milliliters in 1 liter, so I need to write 1,000 to keep this ratio the same. According to the balanced chemical equation, for every 2 moles of sodium phosphate, I need to react it with 3 moles of zinc chloride. And then the molarity of sodium phosphate was 0.20 moles for every 1,000 milliliters. And if you put that into your calculator and you follow sig figs, you should get a number that only has 2 significant figures. Remember, the stoichiometric coefficients don't count as sig figs. Should be left with 66 milliliters of zinc chloride required to react with sodium phosphate. Alright, this is another version of stoichiometry problem with precipitate. And this time, this is a throwback to chapter 9, where we're talking about limiting reactants. This is the same reaction as the previous problem, so you should have the same balanced chemical equation. Three zinc Cl2 plus 2 sodium phosphate goes to zinc 3PO4 2 plus 6 NaCl. We are given 3 moles of zinc chloride. So we're trying to find when we have 35 milliliters of 0.25 molar zinc chloride, and those are reacted with 25 milliliters of 0.20 molar sodium phosphate. how many grams of precipitate, so how many grams of zinc phosphate is formed. So we're trying to get from reactant to products. But again, this is a limiting reactant. We can't just pick one of the reactants arbitrarily. We have to figure out which one's limiting. So we need to know the moles of sodium phosphate as well as the moles of our product in question. We are also given molarity of zinc chloride, 0.25. We're given the volume, which I converted into liters, just to show you can go back and forth. Just need to make sure you stay consistent with all of the units. You're also given 0.025 liters of sodium phosphate and 0.20 molar sodium phosphate. And we're looking for grams of precipitate, which would be specifically grams of zinc 3 phosphate. Alright, so if we go from what we're given of zinc chloride, we want to get to moles of our zinc phosphate. In order to do that, I need to start with what I have, which is actually liters. So zinc chloride was 0.35 liters. To get from liters to moles, I have to do the molarity, which was 0.25. To get from moles of zinc chloride, I need to do the balanced chemical equation, so 3 for every 1 mole of zinc, 3 PO4, 2. And these are going to cancel, and I will be left with 0.0029 moles zinc 3 phosphate. I'm going to do the same thing, but now starting with sodium phosphate, which was 0.025 liters. The molarity of which was 0.20 moles per liter. And then using the balanced chemical equation, for every 2 moles of sodium phosphate, you get 1 mole of zinc 3 phosphate. The moles cancel, the liters cancel, and you end up with 0.0025 moles of product. If I compare the two, I find that the limiting reactant is this one. So that means it's sodium phosphate. So now I can calculate the grams just by converting that into grams. So moles to grams, I do the molar mass. 0.0025 moles zinc 3 phosphate times the molar mass, which would be 386.11 grams per mole. You should get 2 sig figs in your final answer. 0.97 grams. Right, the final type of problem from chapter 12 is acid-base titrations. This is what you're going to be doing in experiment 15, which is coming up pretty soon. So I just wanted to give you a quick overview of these. A titration is a specific type of lab technique where you're using a known amount of a solution, and that known amount of the solution has a known molarity. And we're using this to determine the concentration of an unknown solution, some other solution. So it's to determine concentration. So we don't know the molarity of some other solution. So in order to do this problem, to figure this out in lab, you would set up a system that would look like something like this. You'd have an Erlenmeyer flask that would have an exact volume of your unknown molar, in this case, acid solution. And in a burette, you would have a base with a known molarity. You'd slowly add the base drop by drop into your acid solution and swirl. And you would do this until the second it turns pink in your acid solution, you're going to stop. You would then read the burette. You'd figure out how many mils of base it took you to turn your acid solution pink. And then you would have all of the information you would need to solve for the molar mass of, or the molarity of your HCl solution. So again, when the solution in the flask turns pink, you have reached neutralization. And the neutralization point just means that the moles of base inside the Erlenmeyer flask are equal to the moles of acid. This is important to know because it is an assumption. It's not an assumption, this is actually true. But this is the indication where we stop and we can now actually work with the data given to solve for the molarity of your acid solution. So again, here we're solving for the original acid solution. And this is just a stoichiometry problem. So you'd start with a balanced chemical equation of our reaction. We added sodium hydroxide to HCl, and in the flask a reaction happened where you get sodium chloride aqueous and H2O liquid. And now we can list out what we know. We know our volume of base because we read the burette and it was 22.50 milliliters. Convert that to liters. We know the molarity of our base solution. We know the molar coefficient conversions from our balanced chemical equation. And so we can use all of this to find the molarity of our original acid solution. We also know the original volume of our acid solution was 50 milliliters, which I also converted to liters. So now we can set up the unit conversions. We are also remembering we're working on the assumption that moles of base equal moles of acid. So similar to the previous problem, starting with volume of base, I need to convert it into moles. The molarity of the NaOH is 0.1 moles per liter. You need to use the balanced chemical equation to get from moles of NaOH to moles of HCl. And that was a 1-to-1 ratio. That's NaOH. So the moles cancel, the liters cancel, and I'm left with moles of HCl. We get 0.00225 moles of HCl. I know molarity is moles over volume. The original volume was 0.05000 liters HCl. And in dividing that and following sig figs, I find that the concentration of my original acid solution is 0.450. Should have 3 sig figs. And that is the end of chapter 12. As a reminder, chapter 12, we are only covering sections 1, 5, and 7, and this will be on exam 3, not on exam 2. And I will see you all next week.